What if everything you thought you knew about destruction was wrong? Picture a cosmic dance where chaos isn't the end, it's the spark of something extraordinary. Across the vast expanse of space, stars explode in violent supernovae, galaxies collide in spectacular mergers, and yet, from this apparent devastation, new worlds are born, new stars ignite, and the universe breathes life into the void. This isn't just destruction, it's the universe's way of recycling itself, a grand, eternal cycle of cataclysm and creation that shapes everything we see and everything we are. Think about the last time you watched a fire reduce a forest to ashes. At first glance, it seems like pure loss, but beneath the surface, that fire clears the way for new growth, nourishing the soil and allowing fresh life to emerge. The universe operates on the same principle, just on a scale so immense it's almost impossible to fathom. When a massive star reaches the end of its life and explodes, it doesn't just vanish, it scatters its elements across space, seeding the cosmos with the building blocks of planets, moons, and even life itself. Those atoms forged in the heart of a dying star might one day become part of a distant world or even part of you. This is the hidden rhythm of the cosmos, a symphony of destruction and rebirth that's been playing since the very beginning. Over billions of years, galaxies have collided, merged, and torn apart, yet each collision births new stars, new possibilities. Black holes, often seen as cosmic vacuum cleaners, actually play a crucial role in this cycle, their immense gravity shaping the galaxies around them and even triggering the birth of new stars. It's a universe where nothing is truly lost, only transformed. And as we peel back the layers of these mysteries, we'll uncover how the very fabric of reality is woven from these endless cycles. So come with me on this journey as we explore how the universe recycles itself and discover how even in the darkest corners of space, there's always a spark of creation waiting to ignite. Consider the life of a star not as a single event, but as a chapter in an endless story. Every star begins its journey in a stellar nursery, a vast cloud of gas and dust drifting through the darkness of space. When gravity pulls these particles together, the cloud collapses, heating up until nuclear fusion ignites, and just like that, a star is born. But this birth is only the beginning. For millions, even billions of years, stars burn bright, converting hydrogen into helium in their cores, forging the lighter elements that make up the cosmos. Yet the most dramatic moment comes at the end of a star's life. For smaller stars like our Sun, the finale is relatively quiet. They swell into red giants, then shed their outer layers, leaving behind a glowing ember called a white dwarf. But massive stars, their deaths are anything but gentle. When these giants run out of fuel, their cores collapse in a heartbeat, triggering a supernova, an explosion so powerful it outshines entire galaxies for a brief, dazzling moment. In that cataclysm, elements like carbon, oxygen, and even gold are forged in the unimaginable heat and flung into the void. And here's the incredible part. That destruction is what makes new beginnings possible. Those scattered elements don't just vanish, they become the raw materials for the next generation of stars, planets, and maybe even life. Every atom of oxygen you breathe, every speck of iron in your blood, was once part of a dying star. Even the remnants left behind neutron stars, spinning like cosmic lighthouses or black holes, warping space itself, continue to shape their surroundings, triggering new waves of star formation with their gravitational pull. This cycle isn't just a fluke of physics, it's the universe's way of building complexity over time. Without the death of stars, there would be no planets, no rocky worlds, no chemistry rich enough to spark life. The very ground beneath your feet, the air in your lungs, even the screen you're watching right now, All of it was born from the ashes of stars that lived and died long before our solar system even existed. And one day, when our sun meets its own quiet end, its recycled elements will drift back into the cosmos, ready to begin the cycle all over again. The universe doesn't waste a single atom. It's an endless dance of creation and destruction, where every ending is just the prelude to something new. Supernovae are the universe's most spectacular alchemists, transforming the ordinary into the extraordinary in a single, blinding flash. Imagine a star 20 times more massive than our Sun, burning through its fuel over millions of years. When it finally runs out, the delicate balance between the outward push of nuclear fusion and the inward pull of gravity shatters in an instant. The core collapses at nearly a quarter the speed of light, then rebounds with unimaginable force, a shockwave so powerful it rips the star apart in a supernova explosion. For a brief moment, that single star outshines its entire galaxy, releasing more energy than our Sun will in its entire 10 billion-year lifetime. But the real magic happens in the heart of that explosion. Under the extreme temperatures and pressures, atoms are smashed together with such violence that they fuse into elements far heavier than iron elements like gold, platinum, and uranium. These metals can't form in the gentle furnace of a living star. They're born only in the chaos of a supernova's death throes. Then, like cosmic seeds, these newly forged elements are hurled into space at incredible speeds, riding shockwaves that stretch for light years. Over time, they'll mix with interstellar gas and dust, becoming part of future stars, planets, and even living organisms. The shockwaves themselves are just as vital as the elements they carry. As they blast through nearby molecular clouds, they compress the gas, creating dense pockets where gravity takes over. These collapsing clouds become the nurseries for the next generation of stars, jump-starting the cycle all over again. Without supernova, the universe would be a far poorer place, just hydrogen, helium, and a smattering of lighter elements, with no rocky planets, no chemistry complex enough for life, and certainly no gold for jewelry or uranium for nuclear reactors. Even the remnants left behind play a crucial role. The collapsed core of the star might become a neutron star, a city-sized object so dense that a teaspoon of its material would weigh 1 billion tons. Some neutron stars spin rapidly, emitting beams of radiation that sweep across space like cosmic lighthouses. Others collide in violent mergers, creating gravitational waves and forging even heavier elements in the process. And if the core is massive enough, it collapses into a black hole, warping space-time around it and influencing the growth of entire galaxies. Every supernova is a cosmic reset button, recycling the old into the new with breathtaking efficiency. The calcium in your bones, the iron in your blood, the gold in your jewelry, all of it was forged in the heart of a dying star, then scattered across the cosmos to be gathered up again. Even the atoms in the device you're using right now owe their existence to these stellar explosions. So the next time you look up at the night sky, remember, the darkness isn't empty. It's a vast, interconnected web of destruction and creation, where every ending is just the beginning of something new. But what happens when two neutron stars, those unimaginably dense remnants of supernova, are drawn together in a cosmic dance? The result is one of the most violent and productive events in the universe. Picture two city-sized objects, each packing more mass than our Sun, whirling around each other hundreds of times per second, closer and closer until they finally collide. The impact is so powerful it ripples the fabric of space-time itself, sending out gravitational waves we can detect from billions of light years away. In that cataclysmic moment, something extraordinary happens. the extreme pressures and temperatures far greater than even a supernova force atoms together in ways that create the heaviest elements in the cosmos. Gold, platinum, uranium, these rare metals aren't forged in the hearts of living stars or even in ordinary stellar explosions. They're born in the chaos of neutron star collisions, where the conditions are so extreme that atomic nuclei are smashed together with enough force to build elements heavier than iron. And then, like cosmic gardeners scattering seeds, the explosion flings these newly minted elements outward at nearly the speed of light. They mix with interstellar gas and dust, drifting for millions of years until they're swept up in the birth of new solar systems. That gold ring on your finger, the platinum in a catalytic converter, they were likely born in the fury of a neutron star merger that happened long before Earth even existed. These collisions don't just create precious metals, they also shape the universe around them. The gravitational waves they produce allow us to pinpoint their location, while the accompanying burst of light called a kilonova reveals the presence of freshly forged heavy elements. Some of these events even leave behind a newborn black hole, a gravitational anchor that will influence the growth of its galaxy for eons. What's truly remarkable is how efficient this cosmic recycling system is. A single neutron star collision can produce enough gold to outweigh our entire planet. Over billions of years, countless mergers have enriched the universe with the materials needed for rocky planets, complex chemistry, and life itself. So the next time you hold something made of gold, remember, you're holding a piece of the universe's most dramatic alchemy, a relic of one of the most powerful events in existence. And somewhere out there, another collision is brewing, ready to continue the cycle all over again. Black holes might seem like the ultimate cosmic vacuum cleaners, gobbling up everything in their path with no escape. But these mysterious giants are far more than just destroyers. They're some of the universe's most powerful recyclers, shaping the cosmos in ways we're only beginning to understand. Take the supermassive black holes at the center of galaxies, for example. Their gravity doesn't just hold stars in orbit, it acts like an invisible sculptor, organizing entire galaxies into spirals, ellipticals, or irregular shapes over billions of years. Without that gravitational anchor, galaxies might never take their familiar forms, leaving the universe a scattered, disorganized mess. And here's where it gets even more fascinating. As black holes feed on surrounding gas and dust, they don't just swallow it silently. Some of that material gets superheated and blasted back out into space in colossal jets of energy, stretching for thousands of light years. These jets are so powerful they can heat up vast clouds of interstellar gas, preventing it from cooling and collapsing too quickly into new stars. It's like a cosmic thermostat, black holes regulating the pace of star formation in their galaxies, ensuring things don't get too crowded too fast. But the recycling doesn't stop there. Some theories suggest that when matter falls into a black hole, it doesn't just vanish forever. Instead, it might be compressed and transformed in ways we can't yet fully comprehend. One radical idea even proposes that black holes could be the birthplaces of entirely new universes, that our own universe might have begun inside the singularity of a black hole in another cosmos. If that's true, then every black hole could be a potential doorway to another reality, a recycling plant on the grandest scale imaginable. Even the energy black holes emit plays a role in the cosmic cycle. Hawking radiation, the faint glow predicted to escape from these dark giants, means they slowly lose mass over time. Given enough eons, a black hole could evaporate entirely, returning its energy back to the universe in a final act of cosmic recycling. So while they may appear to be the end of the road, black holes are really more like a crossroads where matter and energy are transformed, redirected, and perhaps even reborn. From shaping galaxies to regulating star formation and possibly even birthing new universes, black holes are proof that in the cosmos, nothing is ever truly lost, only endlessly repurposed. The next time you hear about one of these gravitational monsters, remember, they're not just devourers, they're the universe's ultimate architects of renewal. Galaxies might seem like unchanging islands of stars in the night sky, but the truth is far more dynamic and violent. Across the cosmos, galaxies are constantly drawn together by gravity, merging in slow-motion collisions that last hundreds of millions of years. These encounters aren't gentle dances, they're chaotic, spectacular events where stars are hurled into new orbits, gas clouds are shredded and compressed, and entire galactic structures are rewritten. Yet from this cosmic turmoil, something astonishing emerges, the birth of new stars and even entirely new galaxies. Take the Milky Way and Andromeda, for example. Right now, these two spiral galaxies are racing toward each other at nearly 250,000 miles per hour. In about 4.5 billion years, they'll meet in a gravitational embrace that will stretch, twist, and ultimately merge them into a single, larger galaxy, often nicknamed Milkomda. The collision won't be the fiery explosion you might imagine. Stars are so far apart that most will simply drift past one another, like two swarms of bees passing through the same space. But the real drama unfolds in the gas and dust between them. As the galaxies spiral closer, their immense gravity tugs at these interstellar clouds, compressing them until they collapse under their own weight. These dense pockets ignite new stars in a frenzy of creation, lighting up the galactic cores like cosmic fireworks. Some of these newborn stars will be massive and short-lived, exploding as supernovae and seeding the merged galaxy with even more heavy elements. Meanwhile, the gravitational chaos flings some stars entirely out of their home galaxies, sending them drifting into the void as rogue stars destined to wander the darkness alone. What's truly remarkable is how these collisions shape the future of the universe. Spiral galaxies like the Milky Way and Andromeda often merge to form elliptical galaxies, smooth, featureless collections of older stars with little gas left for new star formation. These elliptical giants dominate galaxy clusters, their quiet golden glow a testament to the violent mergers of their youth, but even then the recycling continues. The supermassive black holes at their centers, once separate, spiral inward and eventually merge, releasing gravitational waves that ripple through space-time. This cycle isn't just some distant spectacle, it's part of our cosmic heritage. Many of the stars we see today, even in our own galaxy, were likely born in past collisions, their elements forged in earlier generations of stars that lived and died in these galactic encounters. And when Milkomda finally forms, it won't be the end of the story. Over trillions of years, galaxies will continue to merge, grow, and evolve, ensuring the universe never runs out of raw materials for new beginnings. So while a galactic collision might sound like catastrophe, it's really just the universe's way of hitting the reset button, scrambling the pieces so the game can begin anew. Dark matter is the unseen hand that sculpts the universe, an invisible force holding galaxies together and guiding the cosmic recycling process on the grandest scale. Though we can't see it, touch it, or even detect it directly, its presence is written into the very fabric of reality, revealed by the way stars orbit the centers of galaxies too fast, or how galaxy clusters move in ways that defy the gravity of visible matter alone. Without dark matter's gravitational embrace, galaxies would fly apart, cosmic gas would never condense into stars, and the universe as we know it simply wouldn't exist. Think of dark matter like the scaffolding of a massive construction site, invisible to the casual observer, yet utterly essential to the structure taking shape. As galaxies form, dark matter's gravity acts as a cosmic net, pulling in ordinary matter, hydrogen, helium, and dust until it's dense enough to ignite new stars. This process doesn't stop at individual galaxies. On an even larger scale, dark matter weaves vast filaments across the universe, creating a hidden web where galaxies cluster like beads on a string. These filaments channel rivers of gas between galaxies, fueling star formation and ensuring the cosmic recycling process never runs dry. Here's where it gets even more fascinating. When galaxies collide, like the eventual merger of the Milky Way and Andromeda, dark matter doesn't just watch from the sidelines. Its gravitational influence guides the chaotic dance, determining how stars and gas are redistributed in the aftermath. Some simulations suggest that without dark matter's stabilizing presence, galactic collisions would be so violent they'd tear galaxies apart entirely, scattering their stars into the void. Instead, dark matter helps orchestrate these mergers, ensuring that even in destruction, there's creation, new stars, new structures, and new possibilities. But dark matter isn't just a passive architect. It may also play a role in one of the universe's greatest mysteries, black holes. Some theories propose that dark matter's gravitational pull could funnel gas toward supermassive black holes, feeding their growth and triggering the powerful jets that shape entire galaxies. Others speculate that dark matter itself might interact in unexpected ways near black holes, perhaps even influencing how they evolve over cosmic time. While we're still unraveling these connections, one thing is clear: dark matter isn't just a spectator. It's an active participant in the universe's endless cycle of destruction and rebirth. So the next time you gaze up at the night sky, remember, what you see is only a fraction of the story. Behind every swirling galaxy, every newborn star, every cosmic collision, dark matter is there, pulling the strings, shaping the chaos, and ensuring the universe never stops recycling itself. It's the silent partner in the cosmic dance, the force that makes all this beauty possible. And though we may not yet fully understand it, one thing is certain: without dark matter, the universe would be a very different and far emptier place. Drifting through the empty spaces between stars, vast clouds of gas and dust might seem like cosmic afterthoughts, fleeting wisps in an otherwise barren void. But these interstellar clouds are where the magic happens. They're the universe's ultimate recycling centers, gathering the scattered remnants of dead stars and transforming them into something entirely new. Picture a nebula like Orion, glowing with ethereal light, not just a beautiful cosmic painting, but a bustling stellar nursery where gravity weaves chaos into creation. Within these clouds, hydrogen atoms float alongside heavier elements like carbon, oxygen, and iron, all forged in the hearts of long-gone stars and scattered across space by supernova or neutron star collisions. Over millions of years, random fluctuations in density create pockets where gravity gains the upper hand. A slight nudge perhaps from a passing star's gravity or the shockwave of a distant explosion triggers a cascade. The cloud begins to collapse, fragmenting into clumps that grow denser and hotter until nuclear fusion ignites deep within their cores. And just like that, a star is born. But the process doesn't stop there. Leftover material swirls around the newborn star, forming disks where planets might one day take shape. Some of these protoplanetary disks contain enough heavy elements to create rocky worlds like Earth worlds where those same recycled atoms might eventually form mountains, oceans, or even life. It's a process so efficient that nearly every atom in your body likely passed through multiple generations of stars and nebulae before becoming part of you. These stellar nurseries aren't just factories for new stars, they're also cosmic time capsules. By studying their composition, astronomers can trace the history of our galaxy. A cloud rich in iron and gold hints at past supernova, while an abundance of rare Earth elements might point to ancient neutron star mergers. Each nebula is a living record of the universe's relentless cycle of destruction and rebirth. And the cycle never truly ends. When massive stars die young, their explosive deaths return enriched material to the interstellar medium, seeding future generations of stars and planets. Even our own sun, now middle-aged, will one day shed its outer layers into space, creating a planetary nebula that will nourish the next wave of star formation. The universe doesn't waste a single atom, it just keeps finding new ways to rearrange them, turning the ashes of the old into the building blocks of the new. So the next time you gaze at a glowing nebula through a telescope, remember, you're not just looking at a pretty cloud, you're witnessing the universe's endless creativity, where every ending is merely the raw material for a fresh beginning. The story of how stardust becomes a planet is one of the most beautiful examples of cosmic recycling. Picture a young star, freshly ignited in a swirling disk of gas and dust. While most of the material feeds the growing star, tiny flecks of heavier elements, silicon, iron, magnesium begin clumping together in the cooler outer regions of the disk. These microscopic grains collide, sticking through static electricity and chemical bonds, growing from specks to pebbles, then to boulders. Over hundreds of thousands of years, these boulders sweep up more material, becoming mountain-sized planetesimals, the building blocks of worlds. Now imagine one of these planetesimals, a chaotic mix of rock and metal, drifting through the protoplanetary disk. Its gravity starts attracting nearby debris, growing larger with each collision. Some impacts are gentle, adding layers like snowfall. Others are violent, melting the surface and releasing trapped gases. Over time, this growing body clears its orbit, becoming a protoplanet, a world in the making. For rocky planets like Earth, this process continues until nearly all nearby material is consumed, leaving behind a molten sphere bombarded by leftover asteroids and comets. These final impacts deliver water and organic molecules, the raw ingredients for life. But where did these materials originate? Every atom of iron in Earth's core, every molecule of water in its oceans, was forged in the heart of a dying star. When massive stars exploded as supernova, they blasted these elements into space, where they drifted for millions of years before being captured by a new stellar nursery. Even gold and platinum, rare treasures on our world, were likely created in the violent mergers of neutron stars, then scattered across the galaxy until they became part of our planet's fabric. The variety of planets we see today, rocky worlds like Mars, gas giants like Jupiter, ice giants like Neptune, all stem from this same process, just under different conditions. Closer to the star, where temperatures are high, only metals and silicates can solidify, leading to dense, rocky planets. Farther out, volatile compounds like water, methane, and ammonia freeze, forming icy cores that can grow massive enough to capture hydrogen and helium, becoming gas giants. Each planet is a snapshot of its birthplace's unique chemistry and environment, a fingerprint of cosmic conditions billions of years ago. Even now, this cycle continues elsewhere in the universe. In distant solar systems, astronomers have observed protoplanetary disks with gaps and rings, telltale signs of planets forming right now. Some of these infant worlds may one day develop continents, oceans, and perhaps even life, all built from the ashes of ancient stars. Our own solar system was once just such a disk, and every mountain, every ocean, every breath of air is proof that the universe doesn't just recycle matter. It transforms chaos into worlds and stardust into stories. Magnetic fields are the universe's invisible architects, weaving through space like cosmic threads that guide the dance of matter and energy. Though we can't see them directly, their influence is everywhere, shaping the paths of gas clouds, steering the debris of exploded stars, and even determining where new solar systems will form. Picture a vast interstellar cloud drifting lazily through the void. Without magnetic fields, it might simply dissipate, its atoms scattered to the winds. But these invisible lines of force act like highways, channeling particles along their length, creating dense filaments where gravity can take hold and ignite the birth of stars. Take the Crab Nebula, the remnant of a supernova observed on Earth in the year 1054. Today, it's not just a cloud of expanding gas, it's a dynamic structure sculpted by magnetic fields trillions of times stronger than Earth. These fields accelerate particles to nearly the speed of light, creating swirling patterns and jets that glow with eerie synchrotron radiation. Without them, the nebula would be a formless puff of debris. Instead, it's a cosmic workshop where magnetic forces help recycle the star's remains into new forms of matter and energy. But magnetic fields don't just shape the aftermath of destruction, they also set the stage for creation. Inside stellar nurseries like the Orion Nebula, these fields act like scaffolding, preventing gas clouds from collapsing too quickly or unevenly. They regulate the flow of material, ensuring that protostars form with stable disks where planets can later assemble. Some theories even suggest that without magnetic fields, the turbulence within these clouds would tear potential star systems apart before they could fully develop. It's as if the universe uses these forces to maintain order amid chaos, ensuring that the ingredients for new worlds aren't wasted. Even on larger scales, magnetic fields play a crucial role. Galactic magnetic fields stretch across entire galaxies, influencing how cosmic rays travel and where interstellar gas accumulates. They may even help funnel material towards supermassive black holes, feeding the engines that power quasars and active galactic nuclei. In galaxy clusters, these fields weave through the hot gas between galaxies, affecting how they collide and merge over cosmic time. Everywhere we look, from the smallest protoplanetary disk to the largest structures in the universe, magnetic fields are quietly directing the show. What's truly remarkable is how these fields persist and regenerate. When a star dies, its magnetic field doesn't simply vanish. It can be amplified and redistributed, seeding the surrounding space with new lines of force. Neutron stars, the dense cores left behind by supernova, often possess magnetic fields so intense they can distort the atoms around them. Some, called magnetars, have fields 1,000 times stronger than ordinary neutron stars, capable of producing starquakes that send ripples through space-time. These extreme objects remind us that magnetic fields aren't just passive guides, they're dynamic players in the universe's recycling process. So the next time you look up at the night sky, remember, the beauty you see is more than just light and gas. It's the product of invisible forces working tirelessly to shape, channel, and renew the cosmos. From the birth of stars to the death of galaxies, magnetic fields are the silent partners in the universe's endless cycle of destruction and rebirth, a proof that even the unseen can leave a visible mark on the fabric of reality. Cosmic rays are the universe's silent messengers, carrying secrets of destruction and creation across unimaginable distances. These high-energy particles, mostly protons and atomic nuclei, race through space at nearly the speed of light, some with energies millions of times greater than anything produced in human-made particle colliders. Where do they come from? Many are born in the aftermath of supernova, where shock waves from exploding stars accelerate particles like cosmic slingshots, flinging them into the void. Others might originate from neutron star collisions, active galactic nuclei, or even more mysterious sources we've yet to uncover. But no matter their origin, these particles don't just travel idly. they play a starring role in shaping the chemistry and evolution of the cosmos. When these energetic particles collide with the delicate molecules floating in interstellar clouds, the results are anything but subtle. A single cosmic ray can smash into a hydrogen molecule, breaking it apart into atoms or ionizing it, knocking electrons loose and creating charged particles that trigger chains of chemical reactions. These reactions form the building blocks of more complex molecules, from simple water vapor to organic compounds like methanol and even amino acids, the precursors to life. In the cold, dark depths of these clouds, cosmic rays act like invisible chemists, stirring the pot of cosmic ingredients that might one day become part of new stars, planets, or even living organisms. Yet cosmic rays aren't just creators, they're also disruptors. Their relentless bombardment can heat interstellar gas, preventing it from cooling and collapsing into new stars too quickly. In some cases, this delays star formation, stretching the process over millions of years. In others, the energy they deposit might actually compress nearby gas, creating dense pockets where gravity can take over and ignite new stellar nurseries. It's a delicate balance. Too much cosmic ray activity, and a cloud might never form stars. Too little, and the chemistry needed for planetary systems might never develop. The influence of cosmic rays extends far beyond star formation. When these particles reach planets like Earth, they collide with our atmosphere, creating showers of secondary particles that scientists can detect on the ground. Some theories suggest cosmic rays might even influence cloud formation on our planet, potentially affecting climate over long timescales. And for astronauts venturing beyond Earth's protective magnetic field, cosmic rays pose a real hazard. Their high-energy particles can damage cells and electronics alike, reminding us that the universe is far from a gentle place. What's truly remarkable is how interconnected this system is. A star explodes in a distant galaxy, sending cosmic rays racing through space. Those particles travel for millennia, eventually triggering chemical reactions in a cloud light years away. Reactions that might one day lead to the birth of a new solar system. Every atom in that system, every planet that forms, every potential spark of life, carries the echoes of that ancient explosion. Cosmic rays are more than just space radiation. They're the threads weaving together the universe's grand tapestry of destruction and rebirth. So the next time you hear about these high-energy particles, remember, they're not just random debris. They're the universe's way of spreading energy, chemistry, and change across the vastness of space, ensuring that even in the darkest corners, the cycle of creation continues. Galaxies are more than just static collections of stars. They're living, breathing ecosystems, constantly evolving in a slow-motion ballet that spans billions of years. Take our own Milky Way, a majestic spiral galaxy that began as a faint whisper of gas and dark matter in the early universe. Over time, gravity pulled these scattered ingredients together, compressing hydrogen into dense clouds where the first stars flickered to life. Each generation of stars that burned bright and died young enriched the galaxy with heavier elements, seeding future stellar nurseries with the building blocks for planets and eventually life itself. But galaxies don't hoard their resources. They're cosmic spendthrifts, consuming gas voraciously to fuel new waves of star formation. Spiral arms act like conveyor belts, funneling interstellar material toward regions where gravity can work its magic. When massive stars exhaust their fuel and explode as supernovae, they don't just vanish, they flood their surroundings with enriched gas, triggering shock waves that compress nearby clouds and jumpstart the next cycle of star birth. Even the smallest dwarf galaxies, often overlooked, play a crucial role in this process, contributing fresh gas and stars when they're absorbed by larger neighbors. Then there are the mergers, spectacular collisions where galaxies lock in a gravitational embrace, reshaping each other in the process. When two spirals collide, their delicate structures are torn apart, their stars flung into chaotic new orbits. But from this chaos comes creation. The violent mixing of gas clouds ignites bursts of new stars, while their central black holes spiral inward, eventually merging in a crescendo of gravitational waves. The result, often an elliptical galaxy, a smooth, golden swarm of older stars, its gas reserves depleted by the frenzy of star formation triggered by the collision. Yet even these seemingly dead galaxies aren't the end of the story. Over time, they may absorb smaller companions or drift through gas-rich regions of space, slowly accumulating new material to fuel a late-life renaissance. Some elliptical galaxies even show signs of renewed star formation, their outer regions flickering back to life as fresh gas cools and condenses. It's a reminder that in the cosmos, there are no true endings, only pauses in an infinite cycle of consumption, transformation, and rebirth. And the elements themselves, they're the ultimate cosmic travelers. A carbon atom forged in a star 12 billion years ago might have been part of a planet in one galaxy, then ejected into space by a supernova, only to be captured by another galaxy and incorporated into a new star, and perhaps even a living organism. Every galaxy we see today is a snapshot in an endless story, where the past is constantly being recycled into the future. The oxygen you breathe, the calcium in your bones, the iron in your blood, all of it has crossed interstellar space, passed through multiple generations of stars, and witnessed the rise and fall of galaxies long before our solar system even existed. This grand cycle isn't just a quirk of physics, it's the engine that drives the universe's creativity. Without it, galaxies would burn through their gas in a few frenzied bursts, leaving behind a dark, sterile cosmos. Instead, the careful balance of destruction and renewal ensures that the universe remains a place of infinite possibility, where every ending is just the first step toward something new. So when you look up at the Milky Way's shimmering band, remember, you're not just seeing stars, you're witnessing a story billions of years in the making, written in the language of recycled stardust. Quasars are the universe's ultimate powerhouses, lighthouses of energy so intense they can outshine entire galaxies. At their core lies a supermassive black hole, millions or even billions of times heavier than our Sun, greedily devouring surrounding material. But unlike ordinary black holes that lurk unseen, quasars announce their presence with a fury. As gas, dust, and even whole stars spiral toward the event horizon, friction heats the material to millions of degrees, transforming it into a swirling, luminous disk. The energy released is so staggering it blasts outward in jets of radiation and particles moving at nearly the speed of light, visible across billions of light years. These cosmic beacons do more than just dazzle, they reshape their surroundings in profound ways. The torrent of radiation from a quasar can heat interstellar gas to such extreme temperatures that it resists collapsing into new stars, effectively hitting pause on star formation in its host galaxy. Entire regions that might have birthed thousands of stars instead remain diffuse and turbulent, their potential frozen by the quasar's relentless energy. In this way, quasars act like cosmic regulators, controlling the pace at which galaxies evolve. Yet their influence doesn't stop there. Those high-speed jets carry more than just energy. They transport heavy elements forged in stellar explosions far beyond their home galaxies, seeding the intergalactic medium with the ingredients for future generations of stars and planets. Some quasars even trigger star formation in distant gas clouds, their shockwaves compressing material just enough to ignite new stellar nurseries. It's a paradox. The same force that suppresses star birth in one place can spark it in another. The most fascinating aspect might be how fleeting quasars are on cosmic timescales. These brilliant outbursts last only tens or hundreds of millions of years, a blink compared to a galaxy's lifespan. As the black hole exhausts its nearby fuel supply, the quasar dims, leaving behind a quieter galaxy forever changed by its passage. The supermassive black hole remains, but its era of reshaping the cosmos fades into memory. We're essentially witnessing the universe's way of redistributing energy on a galactic scale. Every quasar we observe is a snapshot of a critical transition, where a galaxy's central black hole briefly takes control, redirecting matter and energy in ways that echo across space and time. And just like the stars and nebulae we've explored, quasars are part of the grand recycling process, proving once again that even the most violent phenomena serve a purpose in the cosmos's endless dance of destruction and renewal. The universe's grand recycling process seems endless, but what happens when the music finally stops? Current theories paint two very different portraits of the cosmos' ultimate fate, one of quiet fading, the other of explosive renewal. On one hand, there's the concept of heat death, where the universe expands forever until every star burns out, every black hole evaporates, and all energy is stretched so thin that space becomes a featureless void, colder than imagination. No more galaxies, no more light, just a sea of particles drifting farther apart until even time loses meaning. It's a bleak but scientifically plausible ending, where entropy wins and the universe reaches maximum disorder, like a clock winding down to its final tick. Yet there's an alternative vision, one where destruction isn't the end but another beginning. Some physicists propose a cyclical universe where after trillions of years, the fabric of reality itself might collapse in a big crunch, reversing the expansion in a cosmic inhale. Matter and energy would compress into an infinitely dense point, reigniting the conditions for a new Big Bang. It's the ultimate recycling act, the death of one universe becoming the birth of another, like a phoenix rising from its own ashes. Even wilder are theories like conformal cyclic cosmology, where the distant future of our universe, stretched, cold, and empty, somehow becomes mathematically identical to the hot, dense singularity of a new Big Bang. In this model, there's no true beginning or end, just an endless chain of universes where the last moments of one mirror the first moments of the next. Black holes might even play a role in this cosmic reset. Some speculate that the singularity inside them could birth entirely new universes, hidden from our own. But perhaps the most fascinating idea is vacuum decay, a scenario where a quantum fluctuation in the fabric of space-time triggers a bubble of true vacuum that expands at light speed, rewriting the laws of physics as it goes. Everything the bubble touches would be annihilated and reborn under new rules, like a cosmic software update. While it sounds like science fiction, this process is theoretically possible, and if it happened, the universe as we know it would vanish in an instant, only to be replaced by something entirely new. Whether the universe ends with a whimper or a bang, one thing is certain: the story isn't over yet. Right now, we're living in the universe's golden age, a time when stars still shine, galaxies still spin, and the cosmic recycling process continues unabated. Billions of years from now, when the last stars flicker out, the universe may still find a way to begin again. After all, if there's one lesson the cosmos teaches us, it's that destruction is never truly final. It's just the prelude to the next chapter. White dwarfs are the universe's quietest ghosts, stellar remnants that glow faintly with the leftover heat of a life once lived. When a star like our Sun exhausts its nuclear fuel, it doesn't go out with a bang, but with a slow, graceful exhale. The outer layers drift away as a glowing planetary nebula, while the core collapses into a white dwarf, an Earth-sized ember so dense that a single teaspoon would weigh as much as an elephant. Without the furnace of fusion to sustain it, this remnant simply cools over trillions of years, fading from white-hot to red, then finally to an invisible black dwarf, colder than the deepest reaches of space. But even in their twilight, white dwarfs have surprises left to give. Many orbit companion stars in binary systems, and when close enough, their gravity can siphon gas from their neighbors. This stolen material doesn't just vanish, it piles up on the white dwarf's surface, compressed and heated until it reaches a critical threshold. Suddenly, the accumulated hydrogen ignites in a runaway thermonuclear explosion, flaring the white dwarf into a nova that can outshine an entire galaxy for days. Unlike a supernova, the star survives this outburst, only to begin the cycle anew, gathering material until the next explosion. These periodic eruptions aren't just cosmic fireworks, they're vital recycling mechanisms. Each nova scatters fresh elements like carbon, oxygen, and nitrogen back into space, enriching the interstellar medium for future generations of stars and planets. Some white dwarfs even accumulate enough mass to collapse further, triggering a Type 1, a supernova, a blast so uniform astronomers use it to measure cosmic distances. These explosions forge iron, silicon, and heavier elements in an instant, dispersing them across galaxies in brilliant, fleeting flashes. Yet the most intriguing white dwarfs might be the ones with planets. Astronomers have discovered systems where shattered worlds orbit these dead stars, remnants of solar systems that survived their stars' death throes. Some even show signs of water and rocky debris, suggesting that the building blocks of life might persist long after a star's demise. It's a haunting thought. Long after our sun becomes a white dwarf, the cinders of Earth might still circle it, a silent testament to the solar system that once was. In the grand timeline of the universe, white dwarfs are the ultimate slow burn. They'll outlive every other celestial object, surviving long after the last stars flicker out. And though they might seem like endpoints, they're anything but. Each nova, each supernova, even their gradual cooling, ensures that nothing in the cosmos is ever truly wasted. The atoms we're made of might one day find themselves circling one of these dim stellar ghosts, waiting for the universe to recycle them once again. Exoplanets are more than just distant worlds, they're living proof of the universe's relentless recycling program. When astronomers first began discovering planets beyond our solar system, they expected to find simple gas giants similar to Jupiter. Instead, they uncovered a staggering variety: super-Earths with diamond-rich crusts, lava worlds with molten surfaces, and even planets orbiting the corpses of dead stars. What makes these discoveries truly remarkable isn't just their diversity, but their composition: heavy elements like iron, silicon, and magnesium that could only have been forged in the furnaces of dying stars. Take the exoplanet PSR J1719-1438b, orbiting a pulsar 1200 light-years away. This bizarre world is likely the crystalline core of a once giant star, stripped bare by its neutron star companion and compressed into a planet-sized diamond. Its very existence tells a story of cosmic cannibalism, a star that survived its violent death only to be transformed into something entirely new. Then there's Kepler 10c, a rocky world 17 times heavier than Earth, nicknamed the Mega-Earth. Its impossible density suggests it's packed with heavy elements from multiple generations of supernova, a planetary time capsule preserving the remnants of ancient stellar explosions. Some exoplanets might even carry literal pieces of other solar systems. When stars die, their outer layers are blown away, but their asteroids and comets loaded with metals and minerals can survive. These frozen relics might later be captured by new forming stars, becoming part of fresh planetary systems. Imagine a world where a mountain range is made of material from a star that died billions of years before its own sun even ignited. That's not science fiction, it's the reality of how the universe repurposes its building blocks. The most tantalizing clues come from atmospheres. Advanced telescopes have detected water vapor, methane, and even organic molecules in the skies of distant exoplanets. These chemicals didn't appear by chance, they're the products of cosmic recycling, where elements forged in stars combined in the cold depths of interstellar space before being incorporated into new worlds. Some of these planets orbit in the habitable zones of their stars, where conditions might allow those same ingredients to spark life, continuing the cycle in ways we're only beginning to understand. What does this mean for our own place in the cosmos? Every heavy element on Earth, from the oxygen we breathe to the silicon in our computers, was once stardust. Now we're finding that same story written across the galaxy, on worlds so alien yet so familiar. The universe doesn't just recycle matter, it reinvents it, taking the ashes of dead stars and sculpting them into new possibilities. And with each exoplanet we discover, we're reading another page in this grand galactic story of destruction and rebirth. Gravity is the silent conductor of the cosmic orchestra, the unseen hand that sculpts chaos into order. Without its relentless pull, the universe would be nothing more than a formless soup of scattered atoms, drifting aimlessly through endless darkness. It all begins with the tiniest of nudges, a slight unevenness in a primordial gas cloud, a whisper of density where particles huddle just a fraction closer together. Gravity seizes on that imperfection, amplifying it over millions of years until what was once a wispy nebula collapses into the fiery heart of a newborn star. But gravity's work doesn't stop there. Once a star ignites, its gravity holds planets in stable orbits, creating the conditions for complex chemistry and perhaps life to emerge. When that star eventually dies, gravity ensures its remnants don't simply vanish. A supernova's explosive fury scatters heavy elements across space, but gravity gathers them again, weaving them into new stars, new worlds, even new generations of life. It's the ultimate recycler, ensuring nothing in the universe goes to waste. On a grander scale, gravity binds galaxies together, from the smallest dwarfs to the largest spirals. Dark matter's invisible grip forms vast webs where galaxies cluster like dewdrops on a spider's silk. When these galaxies collide, drawn together by gravity's unyielding tug, the resulting chaos births new stars and reshapes cosmic landscapes. Even black holes, gravity's most extreme manifestation, aren't just destroyers. Their immense pull heat surrounding gas triggers star formation and may even seed the birth of entirely new universes. The beauty of gravity lies in its simplicity. It needs no fuel, no instructions, just mass and distance. Yet from that basic recipe springs the entire cosmic cycle of destruction and rebirth. Every atom in your body, every planet in the sky, every galaxy spinning in the void owes its existence to this fundamental force. So the next time you feel the gentle pull of Earth keeping you grounded, remember, that same force, multiplied across the cosmos, is what makes the universe's endless dance of creation possible. Without it, there would be no stars to light the darkness, no planets to harbor life, no grand story of cosmic recycling to tell. Gravity isn't just a force, it's the universe's way of ensuring the show goes on. Dark energy is the universe's most enigmatic architect, an invisible force pushing galaxies apart at an ever-increasing speed. Unlike gravity, which pulls matter together, dark energy operates in reverse, stretching the fabric of space itself. Discovered in the late 1990s when astronomers observed distant supernova glowing dimmer than expected, This mysterious energy makes up nearly 70% of the cosmos. Yet despite its dominance, we still don't know what it truly is. Some theories describe it as a property of space itself, a cosmic constant woven into the universe's very structure. Others suggest it might be a dynamic field, changing over time like an unseen tide. But one thing is certain: its influence on the cosmic recycling process is anything but straightforward. At first glance, dark energy seems like the ultimate disruptor. As it accelerates the universe's expansion, galaxy clusters grow more isolated, their gravitational bonds straining against the stretching space between them. In tens of billions of years, any galaxies not already bound together could vanish beyond the cosmic horizon, their light never again reaching us. Stars would burn out, black holes would evaporate, and the universe could become a cold, empty void, a scenario called the Big Freeze. In this future, the intricate dance of destruction and rebirth we see today would grind to a halt, with matter too scattered to reunite and begin anew. But what if dark energy isn't the end of the story? Some radical theories propose that this force might not be constant after all. Imagine if dark energy's strength fluctuated over time, growing weaker or even reversing into an attractive force. In such a scenario, the universe's expansion could slow, halt, and eventually reverse a cosmic contraction known as the Big Crunch. All matter and energy would rush back together in a fiery collapse, potentially igniting a new Big Bang. It's a breathtaking idea. The very force tearing the universe apart today might one day become the spark of its rebirth. There's another, even stranger possibility: that dark energy could trigger localized cycles of creation within an ever-expanding cosmos. In certain models of quantum physics, the energy of the vacuum might spontaneously decay, forming bubbles of true vacuum, where the laws of physics rewrite themselves. These bubbles would expand at the speed of light, annihilating everything they touch, but within them, entirely new universes could emerge, each with its own rules and constants. Our universe might be one such bubble, born from the dark energy-driven collapse of another. The irony is profound. The same force that threatens to dissolve cosmic structures might also hold the key to their renewal. Whether dark energy leads to eternal silence or cyclical rebirth, its role in the universe's grand narrative is far from passive. It's a reminder that even the most destructive forces can be part of a deeper, hidden balance, one where endings and beginnings are two sides of the same cosmic coin. And as we peer deeper into the night sky, measuring the acceleration of distant galaxies, we're not just observing the universe's fate. We're uncovering clues to whether destruction really is the final word, or just the prelude to another act in the endless drama of existence. The story of our solar system begins not with a pristine cloud of gas, but with the cosmic equivalent of a recycling bin, a swirling mix of stellar ashes and interstellar dust. Every planet, every moon, even the device you're using right now owes its existence to stars that died long before our sun was born. When scientists analyze ancient meteorites, they find something astonishing: tiny grains of stardust, some over 7 billion years old, twice the age of our solar system. These microscopic time capsules, forged in the hearts of dying stars and ejected into space by supernova, are the literal building blocks of our cosmic neighborhood. Take the Allende meteorite that fell in Mexico in 1969. Inside its blackened chunks, researchers discovered minuscule diamonds and silicon carbide grains, materials that could only form in the extreme conditions of a supernova explosion. These grains predate our sun by billions of years, meaning they drifted through interstellar space long before being swept up by the collapsing cloud that became our solar system. It's as if we've found pieces of a demolished cathedral reused to build a new city. But one supernova wasn't enough to create the rich chemical diversity we see today. The mix of elements in our solar system suggests at least two different types of stellar explosions contributed material, some from massive stars that died young in violent supernova, others from aging stars that gently shed their enriched outer layers like cosmic autumn leaves. This stellar recycling program didn't just provide raw materials, it also delivered the spark needed to ignite star formation in the first place. When a supernova shockwave slammed into our pre-solar cloud 4.5 billion years ago, the sudden compression triggered the gravitational collapse that birthed our sun. The evidence is written in the chemistry of the planets themselves. Mercury's oversized iron core, likely inherited from the remnants of a particular type of supernova rich in heavy metals. Earth's abundance of gold and platinum, probably delivered by neutron star collisions that occurred long before our solar system formed. Even the water in our oceans might trace its origins to interstellar ice that survived the violent birth of the sun, later deposited on Earth by icy comets. This cosmic inheritance isn't unique to us. Every new generation of stars forms from the recycled remains of the old, meaning every planet in the galaxy, and potentially every living thing is ultimately made from stardust. The next time you hold a piece of rock or feel the warmth of sunlight, remember, you're touching the final chapter of a story that began billions of years before our solar system even existed, written in atoms that have crossed the galaxy and back. The universe may be young by its own unimaginable standards, but already we can trace the arc of its future, a slow fading of starlight as the era of cosmic construction gives way to stillness. Right now, our galaxy births about 3 new stars each year, a gentle drizzle compared to the torrential downpour of its early history, but this rate won't last. As galaxies exhaust their gas reserves and existing stars lock away material in white dwarfs, neutron stars, and black holes, the fuel for new stars becomes increasingly scarce. Simulations suggest that in 1 trillion years, star formation will have slowed to a trickle, leaving the universe darker, quieter, and profoundly changed. Yet even in this twilight, the cosmic recycling machine won't shut down. It will simply shift gears. White dwarfs, those fading embers of sun-like stars, will dominate the landscape. Though they no longer fuse elements, their immense gravity pulls in stray hydrogen atoms from the interstellar medium. Over eons, this slow accumulation can trigger sporadic nova explosions, briefly reigniting the darkness with flashes of light. These outbursts won't just be cosmic fireworks, they'll return precious hydrogen to space, offering fleeting opportunities for new star formation long after most galaxies have gone dark. Black holes, too, will play an unexpected role in this distant epoch. Though they're often seen as the ultimate end points for matter, even they aren't permanent. Through a process called Hawking radiation, these gravitational giants slowly lose mass, emitting particles and energy back into the void. For stellar mass black holes, this evaporation takes longer than the current age of the universe, but given enough time, even the largest supermassive black holes will dissipate in a final burst of radiation. It's a poetic twist, the universe's ultimate consumers becoming, in their final moments, the last sources of new energy. The timeline for all this is almost incomprehensibly long. Long after the last conventional star has flickered out, brown dwarfs, failed stars too small to ignite fusion, will still collide occasionally, sparking temporary flares. The slow decay of protons, if it occurs, will convert remaining matter into radiation over quadrillions of years. And in the unimaginably distant future, quantum fluctuations might spontaneously generate new particles or even entire atoms in the void, ensuring that the universe never becomes completely empty. What does this mean for cosmic recycling? The elements we think of as permanent, the iron in our blood, the silicon in our rocks, won't last forever, but neither will they vanish entirely. Over timescales that dwarf the age of the universe, even the most stable matter will transform, releasing energy that could, in theory, seed new beginnings. Some models suggest that in a cosmos dominated by dark energy, random quantum fluctuations might eventually spawn entirely new bubble universes, each with its own laws of physics. Whether our universe's story ends in silence or rebirth, one thing is clear: the atoms around us are just temporary waypoints in a journey that stretches far beyond what we can see. So while the night sky may grow darker with time, it will never be truly still. The universe doesn't know how to stop recycling, it only knows how to change the rhythm of the dance. Gamma-ray bursts are the universe's ultimate double-edged sword, blinding flashes of energy so intense they outshine entire galaxies for a few fleeting seconds. Born from the death throes of massive stars or the cataclysmic mergers of neutron stars, these events pack more energy than our Sun will emit in its entire 10 billion-year lifetime into a beam no wider than a few degrees across. For any planet caught in the crossfire, the consequences would be apocalyptic. A gamma-ray burst pointed at Earth from just a few thousand light-years away could strip our ozone layer, bathe the surface in deadly radiation, and potentially trigger mass extinctions. Yet within this destructive power lies a paradox. These same explosions are cosmic alchemists, scattering the heavy elements needed for life across unimaginable distances. Picture a hypergiant star 20 times more massive than our Sun, burning through its fuel at a breakneck pace. When its core collapses, it doesn't just form a neutron star, it triggers a cataclysm so violent it launches jets of plasma at nearly the speed of light. These jets, focused like cosmic blowtorches, punch through the dying star's outer layers and blast into space, creating a gamma-ray burst that can be seen halfway across the observable universe. The afterglow from such an event lingers for days or weeks, fading from gamma rays to visible light, revealing something extraordinary: the fingerprints of newly forged elements like gold, platinum, and uranium, cooked in the unimaginable temperatures of the explosion. But here's what's truly remarkable: these elements don't just stay put. The same relativistic jets that could sterilize nearby star systems also act as cosmic delivery trucks, propelling heavy elements far beyond their host galaxy. Computer simulations show that the particles in these jets can travel millions of light years before finally slowing down and mixing with intergalactic gas clouds. Over time, those enriched clouds become the raw materials for new galaxies, new stars, and new planets. The gold in your jewelry or the uranium in nuclear reactors might have begun its journey in a gamma-ray burst that occurred before our Milky Way even took its current shape. Even the burst's destructive power plays a role in shaping cosmic evolution. By sterilizing regions of space, they might effectively reset certain areas, preventing life from arising too early in the universe's history when heavy elements were scarce. Some theories suggest this could explain why we don't see evidence of advanced civilizations billions of years older than ours. Gamma-ray bursts may have periodically wiped the slate clean until the universe accumulated enough heavy elements for stable, long-lived planets to form. Yet for all their power, gamma-ray bursts are fleeting. The jets last mere seconds, and even the afterglow fades within weeks. What remains are the elements they've scattered and the lessons they teach us about the universe's resilience. These explosions aren't just endpoints, they're catalysts, ensuring that even the most violent events contribute to the ongoing story of cosmic recycling. So the next time you see a brief flash in distant telescope data, remember, you might be witnessing the universe's way of turning destruction into creation, one spectacular explosion at a time. Time is the invisible thread that weaves the universe's grand tapestry, stretching moments into eons and compressing cataclysms into fleeting instants, all depending on where you stand in the cosmos. Consider a single rotation of our Milky Way galaxy. While Earth completes its yearly orbit around the Sun, the galaxy itself takes a leisurely 230 million years to spin just once. Within that vast rotation, stars are born, live, and die, their remains scattered across space only to be gathered up again over hundreds of millions of years, a timescale so immense it dwarfs all of human history. This glacial pace isn't just a curiosity, it's fundamental to how cosmic recycling works. Take the life cycle of a massive star. It might shine brightly for 10 million years, a blink in cosmic terms, but the heavy elements it forges in its core won't become part of new planets until billions of years later. After the star explodes as a supernova, its ejected material drifts through interstellar space at thousands of miles per second, yet even at that speed, it could take millions of years just to reach the next star-forming region. The gold in your jewelry might have spent half the age of the universe adrift before being captured by the cloud that birthed our solar system. Even more staggering are the timescales of galactic evolution. When two galaxies collide, an event that plays out over hundreds of millions of years, the resulting burst of star formation might last just a few tens of millions of years before settling into a new equilibrium. Yet the effects ripple outward for billions of years as newborn stars live out their lives and die, enriching their surroundings for future generations. The Andromeda Galaxy, currently hurtling toward us at 250,000 miles per hour, won't begin merging with the Milky Way for another 4.5 billion years, roughly the same amount of time that's passed since Earth first formed. What's truly humbling is how these timescales stack upon one another. The atoms in your body were likely forged in multiple generations of stars over billions of years, then spent more eons drifting between galaxies before becoming part of our solar system. The oxygen you breathe might have cycled through ancient atmospheres, primeval oceans, and even the cells of long-extinct organisms before reaching your lungs, a recycling process spanning geological eras. Yet against this backdrop of deep time, some cosmic recycling happens in the blink of an eye. A neutron-star merger lasts less than a second, but in that instant, it forges enough heavy elements to seed future solar systems. Gamma-ray bursts unleash more energy in 10 seconds than our Sun will in 10 billion years, yet their afterglows fade within weeks. The universe operates on every conceivable timescale, from the instantaneous to the infinite, proving that destruction and creation aren't about speed, they're about rhythm. Perhaps the most profound lesson lies in recognizing that we're midstream in a story with no clear beginning or end. The hydrogen atoms fusing in the Sun right now were born in the Big Bang 13.8 billion years ago. The carbon in your DNA was forged in a dying star that vanished before Earth existed. And when our planet is gone, those same atoms will continue their journey, perhaps becoming part of a distant alien world billions of years from now. Time isn't just a measure, it's the loom on which the universe weaves its endless cycles of endings and beginnings. Cosmic dust might seem insignificant, tiny specks barely visible under a microscope, but these microscopic grains are the universe's ultimate survivors, carrying the legacy of dead stars across millennia. Picture a single grain of silicate or carbon, no wider than a fraction of a human hair, forged in the turbulent atmosphere of a red giant or the shockwave of a supernova. These particles are far more than space debris. They're the primordial seeds of planets, the hidden architects of solar systems, and the silent couriers delivering the ingredients for life itself. When a star like our Sun reaches its final stages, it doesn't just fade quietly, it sheds its outer layers in a shimmering display, releasing vast clouds of gas and dust into the void. These grains, rich in elements like silicon, magnesium, and iron, drift through the frigid expanse of interstellar space, enduring radiation, magnetic fields, and the gentle push of starlight. Over millions of years, they clump together in cold, dark molecular clouds where gravity begins its slow work. A chance encounter with a passing shockwave, perhaps from a nearby supernova, compresses these motes into denser pockets, triggering a cascade of collisions. What starts as microscopic particles grows into pebbles, then boulders, and eventually the building blocks of planets, but the journey doesn't end there. Some of these dust grains carry something even more extraordinary: complex organic molecules. Telescopes like the James Webb have detected the chemical signatures of water, methane, and even polycyclic aromatic hydrocarbons, carbon-based compounds that are precursors to life clinging to interstellar dust. These discoveries suggest that the raw materials for biology might be scattered throughout the galaxy, hitching rides on dust particles like cosmic hitchhikers. Imagine a grain forged in the death throes of a star, drifting for eons before becoming part of a comet, which then delivers those molecules to a young, water-rich planet like Earth. The universe's dust doesn't just build worlds, it reshapes them. When massive stars die in supernova, their explosions blast heavy elements like gold and uranium into surrounding dust clouds, enriching them for future generations. These supernova remnants, mixed with pristine interstellar material, become the foundation for new stars with rocky planets from the very beginning. Some of the oldest stars in our galaxy, born before Earth existed, contain barely any heavy elements. But thanks to countless cycles of stellar death and rebirth, later generations, including our Sun, inherited a far richer chemical palette. Even now, cosmic dust continues its quiet work. In the Orion Nebula, vast pillars of gas and dust glow under the light of newborn stars, their shadows hiding fledgling solar systems in the making. Across the galaxy, protoplanetary disks swirl around young stars, their dust grains colliding and coalescing into planets. And when telescopes like ALMA peer into these disks, they don't just see featureless clouds, they witness the intricate spirals and rings where dust is gathering, the birthplaces of tomorrow's worlds. So the next time you gaze at the dark lanes cutting through the Milky Way, remember, you're not just looking at empty space, you're seeing the raw materials of creation, the cosmic dust that carries within it the history of the universe and the promise of what's yet to come. These tiny grains, forged in stellar furnaces and scattered by explosions, are proof that even the smallest things can shape the grandest stories. The very fact that we're here to ponder the universe's recycling process might be the most profound clue of all. Think about it: every law of physics, every constant governing the cosmos, seems fine-tuned just enough to allow stars to explode, galaxies to collide, and planets to form from the ashes. If gravity were slightly stronger, stars would burn too fast and die before life could emerge. If nuclear forces were weaker, heavy elements like carbon and oxygen, the building blocks of life, might never form at all. This delicate balance isn't just luck, it's a window into one of cosmology's deepest mysteries, the Anthropic Principle. At its core, the Anthropic Principle suggests that the universe's laws appear perfectly suited for life because, well, we're here to observe them. Imagine a universe where supernova didn't scatter heavy elements, or where black holes devoured everything without recycling material back into space. In those alternate realities, the cosmic cycle of destruction and creation might stall entirely. No planets, no chemistry, no observers. We exist in this universe precisely because its rules allow for the endless recycling that makes life possible. It's like a cosmic version of survivorship bias. We only see the universe's successful experiments because the failures leave no one around to witness them. This idea becomes even more striking when you consider the sheer unlikeliness of our existence. For life to arise, the universe had to get countless things right: the precise strength of the forces that bind atoms, the stability of carbon, the longevity of stars to allow planets time to form and evolve. Even the violence of cosmic recycling had to be just violent enough supernova to seed the galaxy with heavy elements, but not so many that radiation sterilizes entire regions. It's as if the universe calibrated its own chaos to walk a razor's edge between too much order and too much destruction. Some scientists take this further, proposing that universes with different laws might exist in a vast multiverse, each with its own random set of constants. In most of them, the numbers don't add up to life, but in a rare few, like ours, the math works out, and observers emerge to marvel at the cosmic machinery. Whether you see this as profound or merely tautological, one thing is undeniable: our ability to study the universe's recycling process is inextricably tied to the fact that the universe allows such processes to produce beings like us. So the next time you hear about a supernova forging gold or a neutron star collision seeding the galaxy with platinum, remember, you're not just learning about distant astrophysics. You're glimpsing the very conditions that had to align across billions of years to make your existence possible. The universe doesn't just recycle matter, it arranges the chaos in a way that every so often lets stardust pause and reflect on itself. The idea that our universe might be just one bubble in an infinite cosmic foam is both humbling and exhilarating. Picture this: every black hole's crushing singularity, every collapsing vacuum decay event, even the final moments of a dying universe, could be the birthplace of an entirely new cosmos with its own laws of physics. This isn't science fiction, it's a serious scientific hypothesis known as the multiverse theory, where the life cycle of universes becomes the ultimate act of recycling. Take the concept of black hole cosmology, for instance. Some physicists speculate that the singularity at the heart of a black hole, a point of infinite density, might not be the end of matter, but a gateway. Just as our own Big Bang emerged from an unimaginably hot, dense state, the interior of a black hole could spawn an entirely new universe, hidden forever from our own. In this scenario, every star that collapses into a black hole becomes a cosmic matryoshka doll, nesting fresh realities within its event horizon. The iron in your blood, the oxygen in your lungs, might one day find itself part of a new universe's genesis, recycled through forces we can barely comprehend. Then there's the wilder notion of conformal cyclic cosmology, proposed by Nobel laureate Roger Penrose. He suggests that the distant future of our universe, cold, empty, and stretched to near featurelessness, might mathematically resemble the hot, dense singularity of the Big Bang. If true, the end of time could seamlessly become the beginning of a new cosmic cycle, with particles losing all sense of scale and effectively resetting to start the story anew. The remnants of ancient black holes, long since evaporated, might even leave faint imprints, Hawking points, in the cosmic microwave background of the next universe, like cosmic graffiti from a bygone reality. Even quantum fluctuations in the vacuum of space could play a role. Some models of eternal inflation propose that random fluctuations in dark energy might spawn bubble universes with entirely different physical constants. Most would be stillborn, collapsing instantly or expanding too rapidly for stars to form. But a rare few, like ours, might strike the perfect balance between chaos and order, allowing galaxies, planets, and life to emerge. In this view, our universe isn't just recycling matter. It's part of a grander experiment where countless variations unfold across an unimaginable multiverse. The implications are staggering. If true, the elements forged in supernova might not just be recycled within our universe, they could become the raw materials for realities we'll never see. The gold in your jewelry might one day help form a mountain on a planet in a universe where gravity is twice as strong, or where time flows backward. And if black holes truly birth new cosmoses, then every galaxy's central supermassive black hole could be a cosmic womb, nurturing the seeds of future existence. Yet for all its grandeur, this idea leaves us with haunting questions. Could information, the quantum states of particles, the imprint of civilizations, somehow survive the transition between universes? Are there echoes of past cosmic cycles hidden in the subatomic fabric of our reality? We may never know for certain, but the mere possibility transforms cosmic recycling from a local process into something transcendent, a reminder that even in the face of entropy, the universe might always find a way to begin again. The atoms we're made of could have witnessed countless births and deaths of universes before becoming part of us, and they may yet carry that legacy forward into realities beyond our imagination. Ancient civilizations across the globe looked to the skies and saw more than just stars. They saw stories of cosmic cycles etched in the darkness. The Hindu scriptures spoke of endless kalpas, days and nights of Brahma where universes are born, dissolve, and are reborn. Norse mythology described Yggdrasil, the world tree perpetually decaying and regenerating amidst the fires of Ragnarök. Indigenous cultures from the Maya to the Hopi tracked vast cycles of time where worlds emerged, collapsed, and began anew. These weren't just poetic metaphors, they were humanity's first attempts to explain the rhythm of existence itself. Modern cosmology reveals something astonishing. These ancient visions of cyclical destruction and rebirth might contain profound scientific truth wrapped in mythological language. When astronomers observe galaxies colliding, stars exploding, and black holes merging, they're witnessing the same eternal patterns our ancestors imagined, just through the lens of physics rather than folklore. The Big Bang Theory itself aligns with certain creation myths, describing a universe emerging from a singular, unimaginably dense state. But where ancient cultures saw gods or serpents shaping reality, we now understand the forces of gravity, nuclear fusion, and quantum fluctuations as the true architects of cosmic renewal. Consider the similarities between the Hindu concept of pralaya, the periodic dissolution of the universe, and modern theories like the Big Crunch or conformal cyclic cosmology. Both describe a universe that doesn't end but transforms. Even the Norse idea of a world consumed by fire before rebirth finds eerie parallels in gamma-ray bursts and supernova that sterilize regions of space, only to later seed them with the elements for new solar systems. These mythological echoes suggest humanity intuitively grasped a fundamental cosmic truth long before telescopes revealed it, that destruction and creation are two halves of an endless cycle. What's truly remarkable is how these ancient narratives anticipated scientific discoveries about cosmic timescales. The Maya's long count calendar tracked cycles spanning millions of years, while modern astronomy reveals that galactic evolution operates on similarly vast epochs. When the Hopi spoke of previous worlds destroyed by fire and flood before the emergence of the current one, they unknowingly mirrored the scientific understanding that Earth itself has undergone multiple mass extinctions followed by explosions of new life. The universe doesn't just recycle matter, it recycles the very patterns of existence. Yet there's a crucial difference between ancient myths and modern science. Where mythmakers saw purposeful cycles, divine dramas playing out across time, we now understand these processes as the inevitable consequences of physical laws. The supernova that scatters life-giving elements across space isn't a god's deliberate act. It's the natural outcome of stellar physics. Black holes aren't cosmic serpents devouring worlds, but gravitational phenomena that reshape galaxies through predictable mechanics. This doesn't make the ancient stories any less profound. If anything, it reveals how deeply humanity has always sensed the underlying rhythms of reality, even when interpreting them through the lens of their time. Today, we stand at a unique crossroads between these worldviews, with particle colliders recreating conditions from the universe's first moments, and telescopes capturing galaxies in every stage of evolution. We're piecing together a scientific epic that resonates with the oldest human stories. The next time you hear an ancient tale of worlds ending and beginning anew, remember, those storytellers were glimpsing the same cosmic truths we now measure with satellites and spectrographs. The universe has always been recycling itself. We're just learning to read the instruction manual written in starlight. Every atom in your body tells an epic story, one that began long before Earth existed, written in the fiery hearts of distant stars. The carbon in your cells, the oxygen filling your lungs, even the iron coursing through your veins were all forged in stellar furnaces and scattered across the cosmos by violent supernovae. These elements didn't just appear, they were recycled through generations of stars, each explosion enriching the universe with the building blocks of biology. Consider the journey of a single carbon atom. It might have formed deep inside a red giant star, fused from 3 helium nuclei under crushing pressure. When that star shed its outer layers, the atom drifted for millennia through interstellar space until a shock wave from a nearby supernova compressed it into a molecular cloud. There, gravity pulled it into a fledgling solar system where it became part of an asteroid. After billions of years, that asteroid may have crashed into early Earth, delivering its precious cargo to a planet already rich with water and organic molecules. Today, that same carbon atom could be part of a leaf, a drop of ocean water, or even a strand of DNA, proof that life isn't just shaped by cosmic processes, it's woven from them. This connection between stardust and biology isn't poetic metaphor, it's measurable fact. Meteorites like the Murchison specimen, which fell in Australia in 1969, contain amino acids, the molecular foundations of proteins. These organic compounds didn't form on Earth. They're extraterrestrial, forged in the cold depths of space through reactions triggered by cosmic rays and ultraviolet light. When such meteorites bombarded our young planet, they may have delivered the raw materials for life's earliest chemistry experiments. Even the water in Earth's oceans likely arrived via icy comets, frozen remnants of the solar system's birth, carrying hydrogen and oxygen forged in stars that died before the sun ignited. The universe doesn't just recycle atoms, it recycles the conditions for complexity. Supernovae create heavy elements, but they also generate turbulence in interstellar clouds, stirring the pot so new stars form with rocky planets from the start. Neutron star collisions seed galaxies with gold and platinum, but also with radioactive elements like uranium, whose decay heats planetary interiors, driving plate tectonics and volcanic activity, key factors in stabilizing Earth's climate over eons. Even deadly gamma-ray bursts capable of sterilizing entire star systems might play a role in regulating where and when life can emerge, preventing biology from arising too early in regions where heavy elements are scarce. Astrobiologists now search for life's fingerprints across the cosmos by tracing these recycled ingredients. When telescopes detect water vapor in exoplanet atmospheres or methane plumes on Mars, they're following a trail that leads back to stellar explosions. The phosphorus in your DNA, the calcium in your bones, the sulfur in your cells, all were forged in stars that died so you could exist. This grand perspective reshapes how we view our place in the universe. You're not just a passive observer of cosmic history, you're its living continuation, a temporary gathering of atoms that have crossed the galaxy and back. Perhaps most astonishing is how finely tuned this recycling process seems for life's emergence. The specific energies binding carbon atoms allow for stable, complex molecules. Water's unique properties make it the perfect solvent for biochemistry. Even Earth's position in the Milky Way far enough from the chaotic center to avoid lethal radiation, but close enough to benefit from generations of element-rich stars reflects a cosmic sweet spot. The universe didn't aim for life, but its relentless recycling created the conditions where life could aim for itself, transforming stardust into sentience over billions of years. So the next time you take a breath, remember, you're inhaling oxygen atoms that once burned inside a star. When you touch a tree, you're connecting with carbon that survived a supernova. Every living thing on Earth is part of this ancient, interstellar exchange, proof that biology isn't separate from astrophysics. It's the universe's way of knowing itself, a fleeting but brilliant spark in an endless cycle of transformation. Imagine a civilization so advanced that dying stars aren't the end, they're an opportunity. Across the cosmos, intelligent life might not just witness cosmic recycling, they could become active participants in it. Take the concept of a Dyson sphere, a megastructure envisioned by physicist Freeman Dyson, a vast network of energy collectors surrounding a star to harness nearly all its power. While this sounds like science fiction, the underlying principle is pure cosmic pragmatism. Stars are the universe's ultimate power plants, and any civilization facing the heat death of the universe would see them as resources too precious to waste. But why stop at capturing starlight? Enter star lifting, a theoretical process where a civilization extracts material directly from a star to extend its lifespan. A typical Sun-like star fuses only about 10% of its hydrogen before swelling into a red giant. By carefully removing excess mass, a star could burn slower and steadier, lasting tens of billions of years longer. The harvested material could fuel new stellar engines, construct orbital habitats, or even create artificial planets. It's the ultimate act of cosmic stewardship, not just borrowing from the universe, but actively optimizing its processes. The implications ripple outward. If multiple civilizations reach this stage, they might transform entire galaxies into interconnected energy grids. Picture a Milky Way where stars are systematically maintained like trees in an orchard, their lifespans extended through precision engineering. Black holes, often seen as inescapable endpoints, could become power sources via Penrose processes extracting energy from their rotation. Even the debris fields of neutron star collisions might be mined for rare elements, turning cosmic cataclysms into industrial supply chains. Yet this raises profound questions about sustainability. Would such civilizations prioritize balance, ensuring galaxies continue producing new stars naturally? Or would they reshape entire regions into optimized energy landscapes, sacrificing future star formation for immediate need? The universe's recycling system has operated flawlessly for billions of years without intervention, but intelligence introduces a wild card. A single advanced species could alter galactic ecosystems on scales rivaling natural astrophysical processes. Perhaps the most fascinating possibility is how these civilizations might communicate their presence. Instead of radio signals, we might detect anomalies in stellar behavior, stars dimming unnaturally, clusters aging out of sync, or galaxies with suspiciously efficient energy distributions. Astronomers already search for Dyson sphere candidates by identifying stars with unusual infrared signatures. Future telescopes could spot the fingerprints of star lifting in stellar spectra, revealing subtle chemical imbalances caused by mass extraction. This isn't just speculation, it's a lens to rethink our place in the universe. If cosmic recycling is nature's way of sustaining creation, then technological civilizations might represent its next evolutionary phase, beings who don't just adapt to the universe's rhythms, but learn to conduct them. The atoms in your phone or the oxygen in your lungs were once part of stars that lived and died without witness. Billions of years from now, they might pass through hands we can't yet imagine, beings who see the universe not as a fixed backdrop, but as a living system to nurture, optimize, and ultimately transcend. The silence of the cosmos might be the universe's greatest riddle. If the stars are littered with the remnants of ancient civilizations, if cosmic recycling is as universal as the laws of physics, why does the night sky seem so empty? The Fermi Paradox cuts to the heart of this mystery. Where are the architects, the engineers, the beings who have mastered the art of turning stardust into something more? One possibility is as humbling as it is profound. We might be searching for signs of intelligence in all the wrong ways. Consider how a civilization millions of years ahead of us might operate. While we scan for radio signals and laser pulses, they could have moved beyond electromagnetic chatter entirely. Imagine a society that doesn't build Dyson spheres as clunky megastructures, but as quantum energy webs woven into the fabric of space-time itself. Their presence might not announce itself in bursts of radiation, but in subtle gravitational ripples or distortions in dark matter distributions, phenomena we're only beginning to detect. To them, manipulating the life cycles of stars could be as routine as farming is to us, their interventions invisible against the backdrop of natural cosmic processes. Then there's the darker alternative. What if advanced civilizations deliberately hide? The universe's recycling system offers perfect camouflage. A species harvesting comets for water or dismantling asteroids for metals could blend seamlessly into the chaos of planetary formation. Their megaprojects might mimic natural phenomena, a nebula that glows suspiciously efficiently, a black hole emitting oddly structured jets. Even more unsettling is the zoo hypothesis, the idea that Earth is intentionally left undisturbed, a cosmic nature preserve where lesser civilizations like ours can evolve untainted by outside interference. In this scenario, the silence isn't an absence, it's a boundary, but perhaps the answer lies in time. Civilizations could rise and fall in geological blinks, their signatures erased by supernova or gamma-ray bursts before we notice them. The universe recycles matter, but it also erases evidence. A million-year-old Dyson swarm around a dying star might just look like an unusually warm debris field to our telescopes. The ruins of alien cities could be buried under millennia of interstellar dust, their atoms already repurposed into new worlds. We're like archaeologists sifting through a desert after a sandstorm, trying to reconstruct a library from a handful of scattered pages. The most tantalizing possibility, we're early. The universe has existed for 13.8 billion years, but it's still in its adolescence. The peak of star formation is already behind us, and the era of red dwarf stars that will burn for trillions of years is just beginning. Intelligent life might typically emerge far in the future when the cosmos is cooler, quieter, and richer in heavy elements. If that's true, we're not late to the party. We're the first arrivals, pioneers in a galaxy still learning how to sustain civilizations. Yet none of these explanations fully satisfy. The paradox lingers like a shadow on the edge of our understanding, a reminder that for all we've learned about cosmic recycling, we've barely scratched the surface of its implications. Maybe the silence isn't a failure of observation, but a mirror. The universe doesn't just recycle atoms, it recycles questions, leaving each generation to stare up at the stars and wonder anew. Simulating cosmic recycling isn't just about running fancy computer programs, it's about reconstructing the universe's history atom by atom. Picture a supercomputer crunching numbers for months, tracking billions of particles as they swirl through virtual space, collapsing into galaxies, exploding as supernovae, and drifting through eons of cosmic time. These aren't video games, they're digital laboratories where physicists test theories about how the universe transforms chaos into structure. One of the most astonishing simulations is the Illustritingy project, a virtual universe spanning nearly 1 billion light-years. Starting with the smooth soup of matter left after the Big Bang, researchers programmed in the known laws of physics and hit play. Gravity pulls gas into filaments, stars ignite and die, black holes grow and eject jets of energy, all while heavy elements disperse through supernova winds. The results, a stunning match to real telescope observations, from the vast cosmic web to the shapes of individual galaxies. But more importantly, these simulations reveal hidden connections, like how exploding stars regulate star formation by heating surrounding gas, or how supermassive black holes act as cosmic thermostats controlling entire galaxies. The magic lies in the details. Modern simulations can track elements like oxygen, carbon, and iron separately, showing how each generation of stars enriches the universe differently. For example, iron tends to cluster near galactic centers where supernovae are frequent, while lighter elements like oxygen get blown farther out by stellar winds. This explains why planets forming in different parts of a galaxy might have radically different compositions, a detail that could influence where life might emerge. Some simulations focus on extreme events. The Million Core Challenge recreated 2 neutron stars colliding, modeling the gravitational waves, gamma-ray bursts, and heavy element production in one cataclysmic package. The results helped explain why gold is rarer than platinum in the universe, a quirk of nuclear physics that only becomes apparent when you simulate the collision down to quantum scales. Other models explore vacuum decay, testing how a bubble of new physics might expand at light speed, rewriting the laws of reality as it goes, but simulations aren't perfect. They struggle with the sheer range of scales from galaxy cluster gravity down to the turbulent eddies in a single star-forming cloud. That's where zoom-in techniques help, nesting high-resolution simulations inside larger low-resolution ones like cosmic Matryoshka dolls. The Frontier supercomputer recently simulated an entire galaxy at resolutions fine enough to spot individual giant molecular clouds, the birthplaces of stars, all while tracking how their chemistry evolved over 12 billion years. What's truly groundbreaking is how these virtual universes predict phenomena before we observe them. Simulations of dark matter hinted at dark galaxies, invisible counterparts to normal ones, years before telescopes spotted their faint starlight. Models of protoplanetary disks predicted intricate spiral arms, later confirmed by the ALMA telescope. It's as if we're decoding the universe's operating manual by trial and error, one simulation at a time. Looking ahead, quantum computers could revolutionize the field by modeling particle interactions directly, without approximations. Imagine simulating every atom in a supernova, or watching quantum fluctuations spawn entire universes in a processor. Until then, every byte of data brings us closer to answering the ultimate recycling question: how a universe born from nothing but hydrogen and helium became rich enough to make planets, people, and the devices you're using right now, all through the patient work of stars that died so we could exist. From the tiniest speck of interstellar dust to the vast, swirling arms of galaxies, The universe runs on an endless loop of destruction and rebirth, a cosmic economy where nothing is wasted, and every ending fuels a new beginning. Supernovae that tear stars apart also seed the cosmos with the ingredients for planets. Galactic collisions that rip apart spiral structures give birth to dazzling bursts of new stars. Even black holes, those infamous devourers of light, sculpt their surroundings in ways that trigger fresh cycles of creation. Far from being random chaos, these cataclysms are the universe's way of reinventing itself, ensuring that the story never truly ends. What's truly humbling is realizing how deeply we're woven into this grand tapestry. The calcium in your bones was forged in the heart of a dying star billions of years ago. The oxygen you breathe once floated in the void between galaxies. Every atom in your body has survived supernova, crossed interstellar space, and been part of countless cosmic events before finding its way into you. You're not just observing the universe's recycling process, you're living proof of its success. This perspective transforms how we see our place in the cosmos. We often think of ourselves as separate from the universe, mere spectators to its vastness. But the truth is far more intimate. We are the universe experiencing itself, temporary gatherings of stardust that can pause, reflect, and marvel at the journey that brought us here. The same forces that shaped galaxies' gravity, nuclear fusion, the slow dance of dark matter also shape the conditions for life to emerge. The night sky isn't just a display of distant lights, it's a chronicle of our origins. When you gaze at the Orion Nebula, you're seeing a stellar nursery where the next generation of suns is being born from the ashes of the old. The faint glow of the Milky Way is the combined light of countless stars, each a link in a chain of cosmic recycling stretching back to the Big Bang. And somewhere out there, new elements are being forged in collisions and explosions, destined to one day become part of worlds, and perhaps life we can't yet imagine. As we continue to explore, from the depths of particle colliders to the farthest reaches of telescopic observation, we uncover more clues about how this intricate system works. Every discovery, from the heavy metals scattered by neutron star mergers to the magnetic fields that shape galaxy clusters, adds another piece to the puzzle. But the greatest revelation isn't just scientific, it's philosophical. In a universe where destruction and creation are two sides of the same coin, endings aren't something to fear. They're simply the prelude to what comes next. So the next time you step outside and look up, remember, you're not just standing under the stars, you're standing among them, a living part of this endless cycle. And as the universe keeps spinning its story, who knows what incredible chapters lie ahead? If you've enjoyed this journey through the cosmos, let us know in the comments. And don't forget to like and subscribe for more deep dives into the mysteries of space. Until next time, keep looking up.